Okay, so yesterday we finished talking about horizontal transformation, horizontal translations, and I just want to reiterate that real quick because of what it's going to kind of move into a little bit today. If we talked about, like we had a function f of x, let's just say like it's x squared for the moment, okay? And then I want to look at a horizontal translation, then that's going to be like f of x minus c is the way we wrote it in our notes. And if I do that, so create a slider here, and you see then if I'm subtracting, which direction is that moving? Moves it to the right. If I'm adding, which way is that moving? To the left, okay? So what I want you guys to recognize is that no matter what function I'm dealing with, and really no matter what the transformation is, if it's happening to x before you evaluate, so I'm going to add 3.1 to whatever x value I chose before I square things, right? Before I run it through the overall function. If you're doing something to x, whether it's adding or eventually it's going to be multiplying today, if you do that first before you square or square root or take the logarithm or raise it to as an exponential or something like that, then it's a horizontal adjustment somehow. In this case, it's a horizontal translation, a movement, a shift, okay? There are some functions that, like let's say my function is like the absolute value of x. Okay, you see that here, if I'm now, because I am adding 3.1 before I take the absolute value, right? We can see that that is still a horizontal movement. So I'm going to go through a series of functions here that give you a visual of what is happening to x and y, and just kind of what it looks like algebraically, and then make the connection graphically, okay? So start with that. So let's go square root of x. And you see hopefully that a lot of these operations actually create like a grouping for us, right? Our symbol here of the square root, there's a grouping of x minus 8. So it tells us order of operations, do that first. And if I have to do that first before I take the square root, then it's a horizontal adjustment, okay? If we go, I think yesterday I showed you like sine of x. And you see then that that moves that graph left and right as well, correct? Different spots of where we're seeing us add to x or subtract from x before applying the overall sine function in this case. What if we go, let's say f of x is equal to a logarithm. So I'll just say log base 2 of x. Okay. Do you see that even you might not have any idea how to graph a logarithm right now, but do you see that this relationship here is still adding to the x before I run it through the logarithm, and that is still a left and right movement, right? Okay. You guys know what is the inverse of a logarithm? An exponential. Okay. If I look at that, okay, do you see now? This is kind of the one that's a little bit more bizarre than any others that we've seen. The other one's really, if we're adding or subtracting the x, that by default almost puts parentheses around it, right? Here, it doesn't necessarily do that, but it puts it in the exponent, okay? And we see that, you know, by order of operations, you would, if you chose an x value, let's say x value was like 3, you would take 3 minus 0.3, evaluate that first, and then take 2 and raise it to that number. Okay, so you would do an adjustment to x before raising 2 to that power. That is still a left or right movement. Okay, so hopefully that's a visual of where we are going to see adjustments to our x value in several different types of functions. Now, obviously, logarithms, exponentials, I know that our experience with those is limited. And there's an entire chapter devoted to those, okay? And when we get to that chapter, we will talk about these transformations within there again. When we talk about trig and we get into the sine function, the cosine function, we will talk about these transformations within those things again. But here's my thought, okay? And this is why this is designed this way. If we can talk about them holistically first and just say any generic function f of x or g of x or h of x, what you want to call it, and we understand that, subtracting from x or adding to x or adding to the whole thing or subtracting from the whole function or multiplying by a number out in front, how that impacts things, then when we get to a logarithm, we really don't have to spend a whole lot of time on that because we've already generally talked about it with generic functions. Does that make sense? Okay. We shouldn't have to talk about it that much when we get to trigonometry. We'll discuss because it's very important, but the reason I explain that is when I was a student, I always had, okay, how often am I going to use what I'm currently learning, right? You guys do that all the time, right? Okay. How often am I going to use this? How important is this? Because if it's extremely important, then I'm going to take some time and learn it. And what I want to convey to you is that this stuff is extremely important. Transformations are going to be around forever, okay? And if you think about it, it would have been nice that somebody would have explained that to you maybe in like the 7th grade when you guys were taking shapes, when you were taking something, we did a little bit in geometry, but you're taking that shape there and you're moving it up and over, okay? Because that's the exact same thing that we're going to do when we take a function like, let's say f of x is equal to a, let's go this way, x minus a plus c. I don't want to use a. Already labeled that something. bc, let's go x minus d. Okay, so if I take this triangle, move it up and move it over, is that really the same thing as taking that parabola, moving it up, and then moving it over? Does that kind of make sense? Okay, so there should be a direct correlation to what we've already talked about, and maybe since the 7th and 8th grade when you guys were doing it with these translations, okay? And even in 7th and 8th grade, you did stuff like this. You took that shape and you, see here, you reflect that shape over here and ask, okay, well, what happened to these ordered pairs, right? What happened from A to get to A prime, okay? Well, isn't that the same thing as taking this function here, and if I want to reflect over the y-axis, I make that negative right there, and did it flip it across the y-axis? Does that kind of make sense? Okay, so it may seem somewhat new to us, but if we can make those connections to what we've already done in geometry, it's really the same thing. Okay? Today, we're going to talk about vertical stretching and shrinking of graphs. Okay? Well, all that is, if you go back to geometry, if I take this graph right here and I dilate, and we'll go from, in this case, we'll go from 0 to 0, so let's put that point in. Dilate that shape from 0 to 0 by a factor of c. Okay, do we see that, how does A and A prime relate? Okay, A prime sub 1, actually, which is right there. Okay, let's actually make the c value a 2. And let's put this point right there at A. So A is at 5, right? So looking at those two, how do those y values relate? Twice as big, right? You guys remember doing dilations, right? Dilations, all you do is take the ordered pair and multiply it by whatever the scale factor is. Well, that's really all we're going to do today, okay? When we talk about a vertical stretch or a vertical shrink, or I call it a compression, for our functions, okay? And what it says here is if you have a what we call a scalar multiplier, that number right there is referred to as a scalar multiplier, and basically it's a scale factor. Okay, If we want to graph y equals c times f of x, if c is greater than 1, okay, so we're multiplying. So if I multiply anything, start with any number, imagine any number in your head, and multiply it by 2, what just happened to that number you had in your head? Did it get bigger or get smaller? Got bigger, right? Multiply it by 3, would it get bigger or smaller? Bigger, right? Every time you multiply by a number bigger than 1, the number you started with grows, right? Okay. So what that means then is, think about our rule. This rule is saying y is whatever was produced by the rule for your parent function and then multiplied by c. So whatever y is, it just got c times bigger. So let's go over, we'll do an example here. If I have the function, we'll just start with, I like to use x squared. It makes things, I think, easier to understand. It's a good function that we have a good background with. So start with x squared. And we should have then a knowledge of, of x and f of x. If we go -2, -1, 0, 1, and 2, that should be 4, 1, 0, 1, and 4, right? Okay. Now, if I say, I want to look at g of x, where that is 2x squared. Okay, and I'm going to evaluate just like we would have like in Algebra 1. And then hopefully draw a comparison to us never needing to do that again. If I plug -2 in here, you're going to order of operations says you square it first, right? What's -2 squared? 4. And then you order of operations says you have 2 times 4, which turns into 8, right? If I plug in -1 squared, I get 1. Multiply by the 2 out front, I get 2. This will give me 0. That'll give me 2. That'll give me 8, right? What do you recognize about that value there and that value there for the same x value of -2? What do you recognize about the 4 and the 8? Twice as big, right? So what if I did, let's say I had h of x, and I asked you, let's say h of x was 3x squared, and I told you plug in -2. What would be the y value that goes with that? It would be 12, right? You take that number right there that you know from your parent function, and all you do is you multiply it by that scalar multiplier, okay? Because this rule is essentially saying what your y value is whatever it was for x squared multiplied by 3, okay? Or multiplied by 2 or whatever. Does that make sense? Okay, so just kind of demonstrating that graphically for us. If we go f of x equals x squared, and then I will have f of x equals, actually we'll go c times f of x. Okay, so that's what we're looking at. Create my slider for c. And I'm going to try to make some lines here that allow us to make a kind of establish a connection here. So just give me a moment. All right, so if we see our function here, so the orange function is x squared, purple one is 2.7 times x squared. It might make sense to at least let you see that, okay? How do you recognize, now I obviously maybe seeing these values isn't all that obvious, but if I were to take, and we can do this with GeoGebra pretty easily, if I say the x value, the y value of point C, divided by the y value of point B, you see that it highlights there that solution is 2.7. Well, how does that 2.7 relate to our function? It's that constant out in front, right? Okay, so what's that telling me? Is that number right there multiplied by 2.7 gives me that number right there, okay? If we make it let's go to something a little bit easier and do some mental math. I'll go 3 there, and let's move this point down here. So let's put it right there where x is 2. Okay? So on my parent function, we have the point 2,4. We know that from x squared. Well, if I'm looking at 3x squared, then that point is still an x value of 2, but now the y value gets amplified by that factor of 3. So it becomes 4, 12. Or 4 turns into 12. Does that make sense? Okay? And we can see that on all of these points. Okay? So if I know any one of these points off of the parent function, I know its ordered pair, to get its corresponding point on the transformed function, the purple one in this case, all you have to do is take the y value from the parent function and multiply it by 3, and it gives you the y value on the purple one. Is that all right? Okay. Now, that's called a vertical stretch. And the way I visualize a vertical stretch is this idea here. If I were to, like, place your hands, like, right there where my cursor is, and place your other hand right there on the other side, okay? Put your foot right here, and now take your hands and lift your hands straight up. Does it look like that graph would get taller that way? That kind of makes sense? Okay? So it's a vertical stretch that way. Now, if I take a number, how can I make a number through multiplication? So let's say I've got a number like 10. What can I do to 10? What can I multiply 10 by so that it gets smaller? Okay, so a number between 0 and 1. Because if I multiply by a number between 0 and 1, it is effectively dividing, right? So if I take like 10 and multiply it by 1/2, or sorry, divide it by, multiply it by 1/2, that's the same as dividing by its reciprocal of 2, right? Okay, so it cuts it in half. So when you have a C value out in front that is between 0 and 1, okay, between 0 and 1, now we get this thing to be what we call a horizontal shrink, or sorry, I messed that up, a vertical shrink, or a vertical compression. And the idea there is I like to think of like my parabola, and a lot of my polynomial functions, I like to think about this way as they're like springs, or like really, like if you ever take like a piece of sheet metal or something like that, or and kind of bend it, okay, or like bow it out. I think this is like if I would put my hands right here and right there and push down on it, that spring or piece of metal is going to kind of bow out. Does that make sense? Okay. So that is called a vertical compression. Okay. And you can see there that if I take on my parent function a y value of 4 and multiply it by 0.1, it turns into 0.4. Is that all right? Okay. Now, what I'm going to show you here is the comparison of that transformation, which was so we've got either a vertical stretch or a vertical compression, okay? How does that relate algebraically to something like this? If I've got, that purple one is, if I highlight here, you can see that it says it's C times f of x, right? Let's put that C in a different spot. Let's put that C, let's go f, and now C times x. Kind of like that. You see how the C is in a different location now? It's attacking the x before I run it through my function. So just like we talked about at the beginning class, if you add to your x or subtract to your x before you run it through the function, it's a horizontal movement, right? Okay. Well, here, if we multiply by our x before we run it through our function, it's a horizontal stretch or a horizontal compression. It's still affecting the horizontal movement. It's just now a stretch or a compression. So if I hit enter, it's not going to change anything right now, but you can see the difference here because it's where the exponent is now, right? Here, in the purple one, the exponent is only to the x, correct? Now here, the exponent is getting applied to this 1 as well. So when I make this go to like a 2, okay, so the red one here is our parent function, and the other two are a vertical stretch. The purple one's a vertical stretch, and the gray one is actually a horizontal compression. Now here's my question. When I do that, do they both look like they're vertical stretches? Okay, so that gets confusing, right? And because of that, I'm not going to give you any questions that ask you algebraically to navigate whether it's a vertical stretch or a horizontal compression. And likewise, when I go between 0 and 1, okay, they both look like they're vertical compressions, right? But really what's happening here is that one is a vertical compression, but the gray one is actually a horizontal stretch. It's getting pulled out to the sides, okay? What I will ask you to do is be able to determine, based on the position of the C value, okay, algebraically, is that a vertical stretch or is that a horizontal stretch, or vertical compression, horizontal compression, okay? Because the position, I think you should be able to know that that one is a vertical stretch, and because it's 0.4, it's actually a vertical compression. And this one here is a horizontal stretch or compression. In this case, it's a compression, or sorry, it's a stretch, okay? So based on the algebra of the equation, I think you should be able to identify which one's which. It's not going to be until we get to a function like this that we can really see what is happening. So if I look at, let's just look at this purple one and the red one here. So the red one's our parent function, and the orange one. If I take this purple one, can you argue that that is a vertical stretch? Is that very easy to see? That's a vertical stretch. Okay. Now, let me show you the gray one. Is it easy to see that gray one is getting compressed? It's a horizontal compression in this case. Or in this case here, it's a horizontal stretch. Okay. But if I were to put the purple one and the gray one together, would you ever confuse the purple one with the gray one? No. Okay. So these types of functions are referred to as periodic functions, meaning that they do the same thing all the time. Okay, they repeat themselves in a certain time frame or a certain interval, and that interval is called our period. But that is easier to see. Those two compressions or just transformations in general are easier to see when we talk about periodic functions. Okay, there is one periodic function that we might talk about this stuff with. I don't know. Just depends on the time frame that we have, but it's called a greatest integer function. You guys ever heard of that before? Sometimes called a floor or ceiling function. And it looks like that. Okay. Sometimes it's called a step function. It looks like steps, stairs. Okay. Now, if I show you the purple one compared to the red one, does it look like the purple one, like that one there, that little step got amplified by a factor of 4? Okay, this little step here, where B is, got amplified by a factor of 4 to go to C. So that's kind of easy to see that that's a vertical stretch, right? Okay, that is because you can see now the width of the bars. Did that bar get shrunk horizontally? It's comparing that one, where my cursor is, to that one. And then if I take, if this becomes like between 0 and 1, you can see that those get kind of longer. Okay, so you can tell by the length of the segment that it's a stretch horizontally or compression horizontally. So that's a floor function. We'll talk about that eventually. So guys, when I introduce these functions that are maybe new to us or that we don't have a whole lot of experience with, don't get like panicked, because I don't care what the function is right now, okay? We will talk about the basic functions in great detail at some point, but what I want us to understand is that when I say like f of x, it could be all types of different things, okay? But when I ask you something like this, and I ask you to identify what does that 3 do to my function f. So f of x is my parent function, right? It could be anything. And if you want to, If you want to say, okay, well, Mr. Fay said that could be anything. So I'm a fan of letting it be x squared. So if I take that highlighted part and rewrite it as x squared, like that, okay, and now say, okay, well, what happens to x squared if I put a 2 out in front and I put a plus 3 at the end? What's that plus 3 do? Yeah, that's a vertical shift 3 units up, okay? What's this 2 going to do? Vertical stretch. Okay. What if I put a negative out in front? What's that going to do? Over. Okay, so that's an x-axis reflection. What if I put a negative right there on the x? That's a y-axis reflection. Yep. Okay, so the idea here is they're going to give you, generic functions. Like they might say like f of, say x plus a minus d, something like that. And I ask you, okay, well, what does this do here? And that's down d units, right? Does that make sense? Okay. What's that a going to do? And it's plus a. Say it again. To the left a units. Does that kind of make sense on what we're doing there? Okay. Yes.
So when it's a horizontal compression, it'd be 2x and then square all of that.
Yes. So, like if I had like f of 2x plus c or something like that. That plus c is up c units, right? And that 2 then, okay, now it's everything that we do with the x is contrary to what you would think. So if, like, well, when we added x, we added c to x, it moved it left, right? When we subtracted c from x, it moved it right, correct? So you would think that a 2 as a multiplier is going to stretch it, right? But it's contrary to that because you're doing the multiplication first before you run it through the function. So that is actually a horizontal compression. That's the opposite. Okay? And that's kind of what, I'm not going to get into a whole lot of detail with you right now about it, but if you scroll down here to these notes, you see that if c is greater than 1, that you shrink the graph of y equals f of x, so shrink is a compression, by a factor of 1 over c. So basically it means that every x value is getting, before you run it through the function, it's getting reduced by some factor before you plug it in. And that's obviously then going to kind of move things closer, move ordered pairs closer to the origin. Yeah. Let's see here. We'll get to that tomorrow. I want to look real quick before we leave. We've got 2 functions. Actually, 1 function. We're going to do it twice. If I have, let's say, f of x equaling negative x squared plus 3. And I graph that. Okay, then we're going to graph f of x equaling negative x squared plus 3. And this little activity here is going to demonstrate a very important relationship about transformations. How many transformations are occurring to so my parent function here would be what? X squared. So I'm going to graph my parent function x squared, 0, 0, 1, 1, 2, 4, right? And negative 2, 4. So I'm going to graph that. Bless you. And I look at that and say, okay, there's two transformations occurring. Would you guys agree that this minus is this negative here is a transformation and this plus 3 is a transformation? All right, which one do you want to do first? Okay, you want to go plus 3 first. So if I plus 3, what have we talked about plus 3 doing to our function? Vertical shift up. So it impacts the y's, right? So every y value on here is going to increase by 3. So this y value here is going to go to 1, 2, 3. It's going to go right there, right? Okay. This y value here is going to go up to right there. This y value there is going to go, oh, can't count. It's going to go there. This one here, there, and that one there, right? Okay. So that was one. So right now, I would have like x squared plus 3 being those black dots, right? And that makes sense from what we know about x squared plus 3, right? Okay, about vertical shifts. Now the negative says we flip it. So this point here, as a y value of 7, it's going to go now to a y value of negative 7. So 1, 2, 3, 4, 5, 6, 7. Okay. This one here is a y value of 4. So go to negative 4, right? Y value of 3 goes to negative 3. And then I'm going to use the symmetry component to help me get these other points. So right now, based on the order that we did those transformations, that, I think, is x squared, negative x squared plus 3. And I'll put a question marks on that. Okay? So I'm going to come over here now. Because you said we wanted to do the shift first, right? Let's do the shift last. If I start with these points, okay, so that would be my parent function, right? If I reflect first, so if I reflect first, 0, 0 stays 0, 0, right? This red point where my cursor is going to come down here to that one. This one here is going to come down there, right? That one there. That red one right there, right? So that's the opposite of x squared. And that makes sense to what we know what the opposite of x squared should look like, right? And now if we move that up 3. 1, so this point here is going to go 1, 2, 3 to there, right? Let me use x's as my point. This one's going to go up 3. So it's going to go there. This one's going to go up 3, so it goes there. That one up 3. And this one up 3. And I get now that parabola, which I now think is negative x squared plus 3. Can you see the issue that one person might do the order of transformations this way and get this graph, and they might do it this way and get a completely different graph, right? Or are they both right? No, one of them's wrong. Anybody know which one's wrong? Yes, this one is wrong. Okay? And it's because of how we do our order of operations when we substitute. Okay? If I substitute x being 1, you add 3 last, right? Does that make sense? So you impact that y value with that 3 at the end. So when we do transformations, there's an order that I want you guys to kind of commit to memory. And this is on my website. And I'll put this in Schoology as well. But this is under section 2.6 on my website. If you scroll, so this blue box, okay? When you have multiple transformations occurring, this is the safest approach, okay? Do horizontal translations first. Do stretching or shrinking second. And now that stretching and shrinking could be vertical or horizontal, okay? But we're going to focus mostly on vertical. Reflecting third, and then the vertical translation, okay? And to be perfectly honest with you, these first three, are independent of one another. Meaning those first 3 could actually come in any order, okay? It's that fourth one is dependent on the first 3 coming first. Does that make sense? Okay? If you don't do it in that order, it's okay. It is okay, but here's the idea. So if we did this first here, okay, what we would really need to do instead of, so we did the vertical translation first here. We moved it up to get this curve right here first, right? Okay. If you do that first, that's fine, but then you don't reflect across the x-axis anymore because the x-axis actually should have been moved up 3 units as well. And now if you reflect on that dotted green line, does it give you this red curve here? Does that make sense to everybody? So you can mess with the transformations order if you understand that idea that when you shift something before you've done a reflection, that the actual axis of reflection should shift too. Okay, but that's something that people forget a lot. So if you go, I remember the acronym HSRV. Okay, H for horizontal, S for stretch, R for reflect, V for vertical. Okay, and if you can remember that, that will be a tool that will safely allow you to transform any function correctly. Okay, and it should allow us to kind of expedite the process of graphing, especially when we start to learn new functions. Okay, if we can remember, where a certain value in a function, how that impacts ordered pairs. How does it impact the x and how does it impact the y to create a new point in one of those families of functions. I'm going to open up, hopefully maybe around 5th period. I'm not going to have any free time until then. I'm going to open up an assignment. It's not going to be due in the next 2 days. It'll probably at least 3 days, at least Friday will be like the earliest that I make it due. Tomorrow, we'll talk about things called even and odd functions. Which you guys understand symmetry a little bit, right? Mm-hmm. So even and odd functions are just talking about symmetric functions. Really what we're doing here is trying to learn little interesting relationships about relations, okay? For instance, some relations are functions, right? Okay? Some functions are going to be special types of functions, an even function or an odd function. And if it's an even function, that might help me graph it faster. If it's an odd function, knowing that might help me graph it faster. Does that make sense? Okay, so we learn these little relationships that should help us speed things up. So we'll talk about that tomorrow.